Looks like it's a small class today. I noticed all my classes were small, but this is a little extreme, but that's all right. You might have figured out from me sort of chilling at the front here making slides, we happen to finish this chapter just a little bit early, so you will probably be released early on this sort of last Friday before the long weekend. This is a great time for me to remind you that it is a long weekend, so please don't come in on Monday. And I'm hoping that by telling all my classes I won't come in on Monday, because I have definitely shown up on campus when I should not have. And that's just from having zero sense of timing or what day it is, which has only gotten worse as I get older. But so last time we had finished off talking about different types of color mixing, and we had mentioned the difference between additive color mixing versus subtractive color mixing, where subtractive color mixing is what we're used to. That's sort of mixing paint colors, and as we add more sort of paints together, we end up with a darker and darker color. But with light, when we add more and more wavelengths of light, we end up getting lighter. So as we add sort of that blue and green and red, as we get more of our spectrum, then we're going to get closer and closer to white light. And so that's going to be important because it is one of the core concepts for one of the theories about how we view light, or how we view color from light. And so we're going to look at three different theories: the trichromatic theory, the opponent process theory, and then the dual process theory. And they're basically going to be building on one another. So as we've seen with a lot of psychological theories, one comes up and then something else comes up to explain it in a different way, and then we kind of settle on what's most accurate at the end. So that's our roadmap here with theories. But our trichromatic theory is actually a fairly old theory. This was first proposed in the mid-1800s, which is actually quite a long time ago. So you might have seen this referred to as the Young-Helmholtz theory, and that's just because Young and Helmholtz were the two researchers that proposed this theory. But I mostly go with the trichromatic theory, and this is one of those cases where the names actually make sense. So trichromatic, tri meaning three, and chroma meaning colors. So in this case, we're starting off with this knowledge that the human eye has three different types of receptors, and they are differentially sensitive to different light wavelengths. What this means is that we have three types of cones, and each of those three types would react to a different wavelength of light. And so this part you're going to find is fairly consistent, where we have three types of cones, and that's because when you actually dissect the human eye, you can see three different kinds of cones. So that factoid will be part of all of our theories, but what it starts to differ between them on is how they respond to light. So here we're saying, okay, so we have three cones, three types of cones, one that responds to red, one that responds to green, and one that responds to blue, which from our additive color mixing model, so red, green, and blue all together should get us to white, the full spectrum of light, more or less. So that's where that started from, and we're going to add these together to figure out what it is we're seeing in the world based on those three different sensors. And so for a little bit of an idea of how they might work together, we're going to look at this diagram here. And this is a weird one to start with, but to orient ourselves, across the bottom we just have different wavelengths of light. So that's our visual spectrum across the bottom, and it's just telling us at different wavelengths from sort of our blue range into the red range, what wavelength are we looking at. And you might notice that the wavelengths don't line up perfectly with the sort of hand-waved numbers that we were given earlier on. We talked about 400 to 700 nanometers. This gets more precise and goes 390 to 750. And it's just sort of different people cut off at different places. We don't care a whole heck of a lot about numbers, so that's fine. But just in case you were looking at that and wondering why it was different, it's just another thing people don't agree on. For our y-axis, that's really just a measure of intensity. They haven't labeled it, so we don't really care what it is, but higher on that would be more intense responding. And so if we just look at the blue curve, that would be our blue sensitive cone. And so from that curve, we would see a peak at about the 440 nanometers mark. And that says that at that exact wavelength, we would see the most responding from that particular type of cone. And then as we get sort of above or below that in wavelength, we'd see a decline or a drop-off in responding to that signal. But the problem here is if we're just looking at that blue cone, going above or below that maximum point, we can still have the same amount of responding. So 50% responding below is going to be sort of a dark blue color, but 50% of responding above is more teal. So how do we actually tell those apart? And that's where the other kinds of cones come into play. So our brain would look at, okay, so this one type of cone is telling me this, what are the others in the same area saying? So if we're seeing some decent responding from our green or red, then we're probably on that teal side. And if we don't see any responding from them, then we'd be on the dark blue side. So our brain gets to kind of put that together, connect all those dots to figure out what frequency we're actually being exposed to. And so we might notice here that that's all well and good. We can tell the difference in the blues, and there's an issue there where our red and our greens overlap pretty dramatically. And if we were thinking about this practically, the amount of responding with both red and green gets a little bit muddy in that overlapped area. So in the yellow range, sort of yellow, green, yellow, and then into orange, there's a ton of overlap there. And it would mean that it'd be kind of hard to tell different types of yellows from each other. So this theory doesn't do a fantastic job explaining yellows, just because of all of that overlap. If our curves were more evenly spread out, it might be better, and they didn't have a great way of measuring all of this when it was first proposed, so maybe that's part of why, but this doesn't explain the whole picture. It does, however, do a really good job at explaining one particular phenomenon, and that is color blindness. So when people are colorblind, they are typically sort of lacking one of those types of cones. So if trichromatic, for our theory, was looking at 3 different color-sensitive cones, someone who is a dichromat would be missing one of those 3 kinds. They only have 2 kinds of cones. And so people might be red or green or blue insensitive, meaning that they're missing either the red, green, or blue sensitive cones. And so this is kind of a simplified version. When we look at it in more depth, it's a little bit more complex than this, because as we said, this doesn't quite match up with our full theory of vision, but it does a decent enough job to explain why many people who are colorblind tend to be red-green colorblind, which means that they can't tell the difference between reds and greens. So if they're missing their red, or if they're missing their green sensitive cones, it would kind of look almost the same. So it kind of makes sense why this would kind of line up with what we see. And because I find color blindness a really interesting topic, I also have another little website there. This is just for your interest, but it's a website that actually shows you different scenes and filters them to show you what it would look like if you had different kinds of color blindness. And I find this really cool because I have some cousins who are colorblind. And so it took them quite a while to figure out that they were colorblind. It's like, well, how did you not know? Well, you're not trying to tell the difference between things. It doesn't really matter. But yeah, just sort of an interesting little side step there. And it's also, when we talk about colorblindness, it always makes me think of the fact that it is a sex-linked trait, which means that it's a lot more likely to be seen in men than women. And that's just due to the nature of chromosomes, but it tends to be a lot more common in men. And that's why my uncle and all of his sons are colorblind, but none of the women in the family are, which is just interesting to me. So someday, next semester I'm teaching a sensation and perception entire course. I might have to do a family tree that tracks that trait, just for interest's sake. But as we said, so that theory does a decent job of explaining color blindness, and it does a decent job of saying what those three different kinds of cones are doing, but it kind of drops the ball on explaining yellow, and there are other things that it doesn't quite make sense of. So what's the next theory? Our next one is the opponent process theory. And this was proposed a little bit later on, still in the 1800s, but towards the late 1800s. This was proposed by Herring. And again, our name is actually kind of helpful here. Opponent process. It's telling us that we have two opposing actions happening, and that's what's going on in this theory. So the beginning of the theory starts off exactly the same. The human eye has three types of receptors, and they have different sensitivities to different light wavelengths. Exactly the same starting. But again, where we differ is how they respond to those wavelengths. And so here, instead of having one that responds to red, and one that responds to green, and one that responds to blue, now we have those three different kinds of cones, but they respond to pairs of wavelengths. So here we're saying we have one type of cone that will fire in one particular way if it's exposed to red, and another particular way if it's exposed to green. And the reason why this can work is if we scoot back to, that is the wrong way. There we go. If we scoot back to this image here, our reds are on the far left side and the greens are in the middle. And so they're separated enough that if we were seeing both red and green at the same time, it wouldn't actually look like red and green. It would look like what's in between them, which is yellow. So we would never be exposed to pure red or pure green on its own. So we can have that one type of cell that tells us we're on that side or we're on this side of the spectrum, and we don't have to worry about there being overlap. And the same idea with our next one, which responds to either blue or yellow. So our second kind of cone will fire in one pattern for blue and a different pattern for yellow. And again, blue and yellow don't sit next to each other in that spectrum. They're separated, so we couldn't actually see those two at the exact same time in the exact same place. And then our third kind of cone is explained as responding to black or white, kind of the same way that our rods do. So it will detect sort of the presence or absence of light. So that might explain why, even though we only really use our cones during the daytime, we can still see sort of darkness versus lightness, which we would have assumed would come just from the rods. Okay, so that kind of makes sense. It explains yellow, which was our big drawback, so that's great. Another thing, it also explains our after images. And I find this image is hilarious because if you went to school in Canada, you immediately remember this image. It is in every science textbook for elementary schools in Canada, where they ask you to stare at that black dot in the middle. Try not to move your eyes, try not to blink, stare at it for 20 seconds or so, and then look at a blank page or a white wall or something. And when you look away, we see an after image, where the green suddenly looks red and the black looks white, and all of a sudden this weird image here turns into a Canadian flag. So once you've looked away, we see the opposite. And the opposite matches with these opposing processes that were proposed. So our green turns into red. The idea being that when you stare at something green for a really, really long time, those cells would get tired of saying green. So when they stop, they almost overcompensate and then start saying red instead. Same with black and white. So the black looks white because they got tired of saying black, and when they got to stop, it kind of swung the other way, and they said white instead. So our after images can be explained by this opponent process theory. Okay, so the trichromatic theory does a good job of the three types of cones, does a great job of color blindness, it has some drawbacks. This one does a great job of after images, and it explains yellow, but it doesn't explain color blindness. So neither of these is the full picture. So what's actually going on? And for once, we end up with not some random, weird, wacky third idea. What's actually going on is a combination of the two. It's like they took the best of both theories and just put them together. And I love that this actually makes sense after having taught those two separate kinds of theories, because this is the logical conclusion. So our dual process theory involves both processes. We still have three types of cones, and they are each sensitive to different wavelengths. And if we hop to the next slide, we see that those cones are sensitive to blue, to green, and to red, just like our trichromatic theory. But instead of just relying on those, we also want to include that opponent process, because we still have evidence for that. So in our model here, we say, okay, so we have some opponent cells that respond to either blue or yellow, they respond to red or green, or they respond to black or white. And the way they've set it up here is that these cells would be almost like a filter that takes that information from the cones and sort of treats it elsewhere. So here, in order to get sort of that blue and yellow, we get information from our blue cones, obviously. And then to get yellow, if you remember, yellow was that midpoint between red and green. So that would be the overlap between red and green. So our red and green sensitive cones would send their corresponding signals if it was yellow. And then when we send that to the brain, we would have one way of saying it's blue and one way of saying it's yellow. So that explains our after images, but we still have our three types of cones. And we've actually named those cells and identified them now, much, much later after the fact. Those are lateral geniculate nucleus cells, or LGN cells, and you can find them in the retina and or the visual cortex. And they basically do that, translating the raw signal from our cones into that opponent process signal. So they tell us red or green, blue or yellow, black or white. And as you can probably tell, this is one of those topics that we could spend way more time on. And again, I'm teaching an entire course on this next semester. So there is a lot we could go into, but we keep it pretty high level for here. So that is everything we wanted to talk about on that sort of bio-heavy side of things. We've done enough about structures and that sort of thing. Let's bring it back into the psychology side of things, just as we wrap up this chapter. So we're going to look at how we get back into perception. So that was more about sensation. How do the signals come in? But how do we turn it into an actual perception? How do we give it meaning? And that's what we're going to focus on for the rest of the class. The first thing we can look at is depth perception. So how we interpret visual cues to tell us how close or far away an object is. We have two broad categories for depth perception cues. They can be monocular or binocular. Mono meaning one, bi meaning two, and ocular just meaning eyes. So monocular depth cues, they only need one eye. Basically means that you don't have to rely on both eyes functioning and sort of that different position of them for it to make sense. As long as you can see, those monocular cues will show up. For binocular depth cues, we need both eyes, and we're relying on the fact that we have two separate eyes that are located in different places, and our brain can interpret sort of some of the differences in signal between them to make sense of depth. And so we'll go into detail on both of these types of cues, but that's just sort of our basic grounding for it. So some of the most common monocular depth cues, I guess before we get into what they are specifically, a good way to try and think of these monocular cues is if you were looking at something two-dimensional. If you were looking at a photograph or a painting or a drawing, these cues would work because we don't need to be in a three-dimensional world for you to see them. So if you have ever taken an art class, then you've used some of these sort of tricks to make it look like something is closer or further away. So I find it easier to identify the monocular depth cues if I can think about, okay, would this work in a two-dimensional image? So the first of these is a nice simple one, and this is occlusion. And that's the idea that stuff that is closer to you is going to block the things that are further away from view. So my laptop is closer to you guys than I am. So my laptop blocks part of my body because it's closer to you and you can't see through it. So it occludes the stuff behind it. So when we're looking at things, if you see something blocking the view of something else, you know that it's closer to you. We can also look at relative height or size. So if we're looking at two cars or two doorways, and one of them looks larger or smaller, taller or shorter than the other, even though they should probably be the same size, then we might make a sort of judgment that one of them must be closer to us if it looks larger or taller, and the one that looks smaller or shorter would just be further away. This is kind of related to that, the idea of perspective convergence, which is as stuff gets further away, it looks like it's getting smaller. So if you've been in an art class and you've had an art teacher get you to draw that horizon line and a vanishing point, and then you would connect, say, the sides of a road back to that vanishing point. You know that roads don't actually come to a point, but as they get further away, those parallel lines appear like they are converging. So that's perspective convergence. We perceive them as getting together because they get smaller as they get further away. We can also use something like familiar size. We know that humans tend to be about human-sized. So if you see a very small person, they're probably just far away from you. And your brain knows about how big a person should be. So if they're a lot smaller than that, then they must be a lot further away. If they're about the right size, then they must be up closer. And then the last one is atmospheric perspective. And this is actually due to what's in between you and the thing that you're looking at. So this tends to be a lot more apparent over longer distances, but we actually experienced a situation that sort of amplified this. So in the last little while, when it was really smoky, it's not just air between us and whatever we're looking at, then it was also air and smoke. So those extra particles amplified this atmospheric perspective. So the idea is that the further away something is, the less saturated it looks, the less detail that you can see, and sort of the fuzzier it gets. Because when we're looking through air, things get just sort of bent a little bit. So as light travels towards us, it gets buffeted around. And so the further away something is, the blurrier and duller and less detailed it's going to look. So when we had smoke in the air, that happened a lot faster, where you didn't have to see something sort of miles away to notice that it was sort of duller in color. If it was across the street, it looked duller in color. So that's another one of those. All right, and then for the very cool ones, and I guess a little bit easier to visualize ones, are our binocular depth cues. So these are the ones that rely on two eyes. And I always talk about the fact that my father is blind in one eye, so he doesn't have binocular depth cues, and yet he's the one who taught me how to play baseball. So his approach to that is, if you can't tell how far away it is, just throw really hard. So not necessarily the best approach, but it does work. So with these binocular depth cues, we're relying on the fact that our eyes are in slightly different positions. Kind of like when we were thinking about auditory localization, our ears are on opposite sides of our head, and so we can kind of tell where things are located based on when they arrive at our ears. With our eyes, we rely on the fact that things look a little bit different whether you're looking at it with your right eye or your left eye. So the first of these terms is retinal disparity. So objects are going to project slightly different images on our eyes depending on which eye is looking at the item. Easiest way to envision this is if you put your finger in front of your eyes and you close one eye or the other. And you'll find that it kind of looks like your finger moves back and forth just a little bit. And the reason for that is your left eye is seeing it a little bit to the right, and your right eye is seeing it a little bit to the left, and so it's looking just a bit different. So there's disparity or not matching between the image that's being projected on the retina of each of your eyes. And so our brain will take these slightly different views, these slightly different perspectives, and figure out how different are they. The more different they are, the closer the object is to you. The less different, the further away it is. And similarly, we can rely on convergence. So as an item gets closer and closer to you, if you've ever done this to try and look cross-eyed, where you try and look at the tip of your nose, that works because your nose is very, very close to you. And so your eyes have to look inward to see your nose. So things that are closer to you cause greater convergence, where your eyes bend inward to look at that central item. And the further away it is, then your eyes can look sort of parallel to each other out to that object. And again, our brain can pick up on those signals of how much sort of inward bending versus outward bending our eyes are doing and determine about how far away it is. And all of these cues are things that are going on in the background. We're not necessarily aware of all of these processes, but it is something that our brain is doing and tracking and has learned from experience with our environment as we've grown. To mess with some of these cues, when I was younger, I needed glasses but didn't say anything for 2 or 3 years, which was interesting because I continued to play baseball. And then I got glasses, and that corrects the amount of bending with the light entering your eyes. And for the first probably 6 months after getting glasses, it had messed with all of these cues so much that I had trouble telling how far away things were. I got hit a lot in baseball because, you put your glove here and the ball's over here. And so it was one of those things where it didn't seem like a big difference, but it was a big difference. And so my brain had to relearn where things were and how stuff was moving together. So we're really good at this, but small things can really negatively affect it. All right, so for more types of processing, we're going to look at how we can assemble information. So not just visual cues in general. This doesn't just apply to visual stuff, but it's easiest to talk about in terms of visual stuff. So when we look at processing, we can call it bottom-up processing or top-down processing. Bottom-up is going to start with the simplest details. So that's when we start with individual features or elements of a stimulus, and we sort of put them together and try and make sense of them as we assemble them together. So maybe you're reading a word for the first time. You've never seen this word before. And so you're going to look at the order of the letters and you're going to sound out each one together. And as you put them together, maybe it starts sounding a little bit familiar. And eventually you have that aha moment where you recognize the word based on the sounds that you've put together. In contrast, top-down processing is when you can use previous experience and sort of your base knowledge of a situation in order to kind of shortcut to the answer. So if you're looking at a word that you've seen many, many times before, maybe you're looking at your name. You don't have to look at each individual letter. You don't have to sound it out. You know the shape and appearance of your name. You instantly know what it is and you can move on. If you are like me and you have trouble typing things in the right order, maybe you're going to take a moment and pause and make sure that the E and the L aren't switched in your signature when you're signing off from an email. So we'd have to go from, yes, it looks like my name, am I sure? Okay, now we can move on. So bottom up starts with your base features and we build them up to recognition. Top down processing starts with, we're pretty sure we recognize it. We can double check if we need to, but we're kind of cutting corners and using our base knowledge to figure things out. And then we can start looking at sort of applying this. An exit sign would be a great example of top-down processing. Every time you see an exit sign, you don't have to think about the individual elements. You don't have to think about the fact that an E has a vertical line and then the 3 horizontal lines, and then the X is the 2 crossed lines. You would look at a 4-letter word that's glowing red and is near a door, and you'd automatically say, oh yeah, it's an exit sign. You wouldn't have to read it and figure it out. So we could go with our top-down processing. We might want to double check that it actually says exit and that it's pointing us towards a door, but not necessarily every single time. The figure on the left is more of a bottom-up kind of processing situation. And this is the first of our weird optical illusions that we're going to look at very, very briefly here. But if we start looking at the individual elements of that image, it's like, okay, so we have an eye and we have a head, but then we get some ambiguity. Is that a beak or are those ears? Is it a duck or a rabbit? And this is one of those situations where when we can't come to sort of that hard conclusion, when we can't be positive if it's a rabbit or a duck, we're going to start hopping between the possible solutions. And we'll start seeing more of this with other optical illusions on the next couple of slides. But first, I want to take a brief detour into talking about Gestalt psychology, or specifically the Gestalt principles of form perception. And so Gestalt psychology is really focused in on the fact that humans have this amazing capacity to perceive a lot more from a situation than the individual elements might imply. So we tend to look at a scenario as a whole, and we tend to be able to sort of derive meaning from it. So in this case, the whole is worth more than the sum of its parts. And so this is just referring to the fact that when we look at stuff, we tend to imply meaning, or we tend to make assumptions that are sort of above and beyond what's actually there. And so we're going to look at some of these principles that illustrate which ways we tend to stick stimuli together, which way we tend to look at things, and then we'll kind of get a feel for ways that humans have these shortcuts to look at things as a bigger piece. And so for the first of these, it has its own slide, and this is our figure-ground relationship. And this is referring to the fact that people are really, really good at deciding what is the central focus of a situation, of an image, of an environment, and what is irrelevant background stimulus. So if we were looking at a painting, we would focus in on a figure, a person standing in that painting, before we tried to look at the background as a whole. So we focus on individual elements that are probably closer to us and something that we could interact with. And then we will eventually consider sort of the situation that we're in. Then we'll look at the background if it's important. So we're really, really good at deciding what that central figure is and what that background is. But again, if we have ambiguous setups, we can run into issues. And so these here are some optical illusions that mess with our ability to categorize what is the figure and what is the background. So in the middle, is it a chalice on a black background, or is it two silhouetted faces on a pink background? And because there isn't a right answer, we're going to kind of flip between those two possible solutions. On the far right, we have, is it a face or is it a landscape of a person walking in a field? And then the last one on the left here is the one that always throws me. I can never see the second option for this one. It's, is it a young woman looking away, or is it an old woman with a headscarf? And I can never see the old woman. I only ever see the young woman, but I have taught this course a number of times, and I always use this one, and I've been reliably told that there is an old woman in the image somewhere. So maybe we just have to stare at it for an extra long time. But this is one that every year I come back to it and I'm like, are we sure? But Google says so and our textbook says so, so we'll go with that one. But yeah, so this is one of those cases where when it's ambiguous, when we can't quite decide what's going on, our brain will kind of hop between those options. And sometimes when you can only see one or the other, you'll only see that initial image. But as soon as you recognize the second one, it's going to jump between the two. It'll flip back and forth between them because neither is more correct than the other. So just one of those fun little things with optical illusions. So the next 4 principles actually have their own slide, and I'm going to talk about those separately, but I do want to talk briefly about the last one, which is the principle of common fate. And that's because I hadn't seen the principle of common fate until this year. And it doesn't have a fantastic image that helps illustrate it. It's more of you need a visual for it. But for this one, it's basically the idea that if things are moving and acting together, we tend to perceive them as a unified whole. So the fantastic way of explaining this is, think of a flock of birds. If you've ever been to the East Coast and you've ever encountered starlings, they form massive flocks called murmurations. They tend to have thousands and thousands of birds together, and they tend to move in very predictable, unified patterns. So when we look at that moving flock of birds, we tend not to see individual birds. We tend to see a larger, mobile shape that's kind of moving across the sky. So that's that principle of common fate, where once they're moving together and once they're sort of unified like that, we treat them as the same object, even though they're clearly not. And we'll see similar concepts with our other principles, and those each have their own animation or image here. So for similarity, we can look there at what could be perceived as a whole bunch of circles, or we might start grouping them based on similarity. Do we see a triangle made up of small circles and maybe another triangle made up of those 3 large circles? It's a lot easier for us to consider things that are similar to be the same, to treat them as one. So we'd see a triangle made up of those small circles because they're all small circles and therefore the same. For proximity, things that are closely located to one another in space also tend to be associated with one another. So in this case, instead of seeing sort of 3 small lines and 3 long lines, we would see 3 pairs of lines. So 3 pairs that have 1 small and 1 long line. And that's because they're closer to each other than they are to the sort of other small lines or the other large lines. So we group things by proximity because when we encounter things that are close together, they tend to be associated with one another. Sometimes. For our principle of closure, we have a tendency to sort of continue and fill in for missing information. And this can kind of go back to that idea of occlusion. So when I'm standing at the front of the room lecturing, you can only see my upper body. But you don't assume that I'm a floating upper body. You assume that you just can't see the rest of me. So I'm human-shaped, but you're only seeing this part. So that would be the same thing with this circle. We'd assume that it's a circle, and we're just not seeing the whole picture. So it's probably a full circle, but some of it might be missing. So we fill in that gap, we close that figure to sort of finish the pattern. And that's very similar to our idea of continuity, where we tend to see things as continuous whenever we can. So we would likely see 2 lines, one that goes from A to B and one that goes from C to D, rather than 2 discontinuous shark fin shapes that go from, say, A to the middle to C and then D to the middle to B. Those continuous smooth lines are a little bit more likely, and that's how we tend to view that information. So this is just about how we, when we look at things quickly, when we're giving it a quick glance, this is how we would quickly classify objects and how we would sort of briefly stick them into categories and start perceiving them. We can, of course, look at these in more detail and make other conclusions, but these principles are all about what's our default? How do we tend to categorize things? How do we put things together? And these tend to be pretty consistent across all people. And the last thing I want to talk about are perceptual constancies. And these are going to be very closely related to everything we've talked about so far. But this is all about the idea that we assume that things in our environment tend to be fairly stable. So even though stuff looks like it's changing, that's not necessarily likely. And so the first of these that's kind of going to illustrate the point is our constancy of size. So when we look at that image towards the middle, we see one person sitting in a chair close to the camera and one person who's sitting in a chair further from the camera. We don't see them as one being larger or smaller. We've used all of our monocular cues to figure out that one's probably closer than the other. So the guy in the background isn't actually that small. But if we used Photoshop to move the guy in the background up to the foreground, that looks like it's absurdly small. It shouldn't be that small. That's even smaller than what it is in the other image. But if you measured them, they're exactly the same height. So by moving him out of the context, by shifting him from that background and moving him to where he would be closer to us, we kind of drop off that further away things tend to be smaller, and he looks extra small in that image on the right. We can also look at things like shape. So if you're having a conversation with a friend and they're facing you sort of face on, and then they turn to the side, their face changes shape. But you don't assume that it's because their face is morphing and changing. You just assume it's because you're seeing a different angle of their face. So the shape isn't actually changing, your perspective or the angle that you're viewing it from has changed. The next two kind of go together, so brightness and hue. This is the idea that, so standing here under these awful fluorescent lights, my sweater looks to be this specific color. If we went outside under sunlight, it would look a little bit different. It might be brighter or darker, or it might look a little bit sort of more green or less green, depending on what wavelength I'm standing under. So I don't assume that I have some magical color-changing shirt. We just assume that the environment, the light sources are changing. So we assume constancy in shape or in color and brightness, and it's just sort of the other aspects that are changing. And then the last one is location in space. And so this is the idea that when I'm moving, I know that I am the piece that is in motion. I don't assume that as I'm walking towards a desk and that desk is getting larger, I don't assume the desk is moving towards me. I know that I am moving towards it. And I actually had a student in my last class who made a point about this. So if you drive and you've ever been stopped at a light and your foot is on the brake and the car next to you rolls forward and you panic for a second wondering if you're moving backwards, that's that location in space constancy messing with your head, because you assume that you are the one that is moving, but by them moving when they shouldn't be, they've kind of thrown that constancy off and used a little bit of an optical illusion in that situation. But those are the major points I wanted to talk about. This is one of my favorite chapters, and we could spend forever on optical illusions, but that gives us a good starting point. And we'll talk about more of some of these sort of putting stuff together when we start getting into things like consciousness, because I believe we also talk about attention there, and that'll relate to a lot of this as well. But we are finished the topic. We will come back on Wednesday, and we can finish off, start off the next chapter. And I don't actually remember what the next chapter is.